And looks like it's time. Welcome back, everyone. So we're on week 4, and I guess the big comment about that is after Thursday's class is over, we're 25% done with the entire semester, so we're definitely getting through it. Any questions that folks have today to start us out? Okay, well, what we did last week was we were working in through chapter 3, dealing with equations of the line. We finished off section 3.1. Section 3.2 was dealing with more issues about equations of lines, the slope-intercept form, and we nearly finished section 3.3. We didn't quite get there, so I made the due date for that section a week away from today in the Newton homework system. Here, the new equation we were looking at was the point-slope form of the line, and that's where we're going to start today. After that, we're going to be handling 2 lines at the same time. That's going to be our chapter 4. Other big announcements are quiz 2 is going to be due next class, so these will always be due on Thursday. I'll have quiz 3 posted down below here when we come back on Thursday. I might post it early on Wednesday just so I can get ahead of my Thursday day. It's usually a busier day for me on Thursday. And also, our first exam is coming up next Tuesday. On Monday morning, I emailed everyone in the class to give you instructions on how to schedule your exam. Some folks have indicated to me they would prefer to test in the Pocatello Testing Center. Some people are in the Idaho Falls Testing Center. And still other people are closer to like the Meridian campus. And I sent you a direct message through the Canvas system telling you how to schedule your exam. Anyone have any questions about that so far, your exam, scheduling your exam? Okay, well, here's the official information on our first exam 1. This will be next Tuesday. It's a 75-minute long exam. And because this is an online class, we won't actually have class on Tuesday. This will just be a blocked out day for people to take care of their exams. Some people might actually test right at 6 p.m., but you're welcome to schedule your exam for any time of the day that just fits in well with your schedule and the testing center's availability as well. So sooner you fill in that testing center link, the sooner you'll know your official time that you'll take the exam. The exam is closed book and closed notes, but you're allowed to have a scientific calculator such as the TI-30XA. So don't forget to bring your calculator. There'll be a couple problems where it'll be nice to have, but I didn't write any exact problems where the instructions said, put this in your calculator, round to a certain decimal place. We haven't done too many like those just yet. First problem like that is really going to be section 4.3. But still, it's good to be in the habit of having your calculator ready when you're doing homework, bringing it to your exam, so you're just already in that pattern. It'll be a familiar thing you do into exam 2, bringing in your calculator when you really need it. So that's going to be our exam next Tuesday. And to prepare for the exams, it's only going from the first section 2.3 up to section 3.3. So the section we're about to finish up today. So I'm not going to extend it into the chapter 4 material, mainly because my thought is we're learning that just this week. It's kind of too soon to put it on exam already on next Tuesday. I want you to have a chance to do these problems, work them out in the Newton Alta homework system, do a quiz on some of the content here, for example, before it shows up on an exam. So sections 4.1, 4.2 are going to be on exam 2, not exam 1. So these are the sections for our first exam. You can take a look at the problems down here, the sample exam problems. In fact, let's just open it up. Here's what it looks like. This is my attempt to show you what an actual exam would look like in terms of the type of problems, the amount of problems. It could be something about like this. So sometimes it looks like I have multiple versions of problem number 3. That's kind of weird, but all good problems. These are the kind of problems that we've been working all along in the course up to the date. And if you go to the second page, here's where I have some of the solutions. Some of them hand jotted down. I don't know how to type out a graph in Microsoft Word, for example. So that's what the sample exam first version looks like. It's just a PDF document that you can print out, take some ordinary notebook paper, start solving problems and see how you're doing on those. Any questions at the moment about the exam or the sample exam below?
How do Pocatello campus students schedule their exam?
So what I did was I sent you a link that gives you a little calendar that you open up. In that calendar, you'd be able to schedule that exam. And let me see if I can pull that up. Let me see here. Now that you mentioned that, thanks for asking about it. I'm going to go into my inbox here to where I sent out that message. So I guess that should be under sent. And this would have been to, let's see, possibly this one right here. So this one is at the ISU ISU exams at the testing center. So this would be pretty much how you'd be booking the exam. So I sent you an email through Canvas. It pulls up a little scheduler like this, and then you would select the date. Let's see here, Tuesday. The duration is going to be an hour and 15 minutes for a 75-minute class. And then you would just select on a time. Then after you do all that, it'll have a little reminder here. And then you would just fill out that information. So whether you're at the Idaho Falls Testing Center or the Pocatello Testing Center, like you asked about, this is pretty much what it's going to look like. Does that make sense? Does that make sense so far with that question, Clay? Okay. And once again, it's an email that you should look for in your Canvas. I think it also sends an email also to your ISU email when I send you something into Canvas, just as a reminder you've gotten a message. At least that's how it works on my end. Correct me if I'm wrong on that. But if you lose track of that, don't hesitate to just email me and I can resend it to you. So if you have any questions further when you're looking for that link, possibly say tomorrow morning or something like that, filling out this form, any questions come up, don't hesitate to reach out. I'll be very happy to help. Other questions at the moment? Okay. Well, this is the exam content going up to section 3.3, starting on day one up to what we're about to finish today. We just have one less problem side here. You can find sample exam one problems here. And for second version, this was asked in class on the very first day. You can go back to the homework system and it says practice exam one has started as due on December 14th. This is just the second version of a practice exam. Some people might want more problems to take a look at within the homework system itself. There's no credit for this, so if you ignored it, it's not going to directly hurt your grade. But if you want to practice more problems, this is a great place to go into. You can click on View Assessment to get into it. Click on Start. You can repeat this as many times as you would like. And again, it's not something you have to do. And if you do it, it's not going to hurt your grade directly. So let's click on Start just to see what it looks like. Looks pretty much like this, almost like doing homework problems, except there's just a long list of problems. And these are more just similar kind of problems that we've been doing throughout the course. Some of them are pretty quick. Some of them take multiple steps, like question 8. If you provide your answer, let's just put in something right away. This is probably wrong just to see how it goes. Well, it looks like if you provide your answer, it's kind of like a real exam where you have to give answers to everything, then click on submit, and it'll tell you how you did on each problem. It'll show you if it was right or wrong, what the correct answer was. You can get step-by-step information on how to solve it and all that kind of stuff on this practice exam. So let me get out of there. That's what this is all about. So when you go to your homework system, it's at the very, very top. And I'll be doing that for exam 2, exam 3, and for the final exam as well. Well, we'll talk more about the exam as we're on our Thursday's class. But any questions at all so far, folks, about the exams or otherwise? Okay, well, let's get started with today's work then. We're in section 3.3. And this is the problem we finished before going on to our deserved weekend at the end of class last Thursday. Let's just look at some key elements of this, just as a quick mini review as we are getting warmed up to doing math again back from the weekend. The problem gave us two pieces of information. The fact that it went through this point right here, and the fact that our line that we're going to give an equation to is parallel. It's kind of rough reading this. It's part D, and the original question said this: find an equation in slope-intercept form for the line satisfying the following information. So that's what the actual instructions were. So coming back down, we want to find the equation of the line that went through that point and is parallel to this other line. So first thing we want to do is find the slope that we would have. We took this line here, solved for the y variable, and this gave us the slope. So we just copied down the 0.14 to here, the slope. Because we said it's parallel, we copied directly down. Our line had to have those two features. So once we knew the point and the slope, we used this formula. Put that in brackets. This formula is the point, slope, form of a line. Using that formula, we had three things we had to substitute in. We had to put in information for y1 and x1. That's the point part of the point slope forming the line. And so that's why we have a 4 and a 1 directly imported there. After we made those two substitutions, the next thing we had to do was put in the slope. That's the slope part of the point slope form of the line. Our slope was a half, so we just dropped a half right where m is in that arrow. Then the last thing we had to do to fully solve this problem is we had to solve for y. So this is now in slope intercept form. And it's really common in instructions in the homework system, on exams as well, to say, take your equation, solve for y, to put it in slope, not slop, but slope, let me put the E there, to put it in slope intercept form. So the problem was over once we got to that stage there. Well, we have one more problem similar to this one, but I felt like it was a good idea to just highlight the formula we used, the process we went through, how we took the given information and dumped it into the formula. We'll do something very similar on the very next problem. Any questions first about this one? Okay, it's hard to see a problem when the whole process is just right there on paper like we're looking at right now. All the steps are there, including the cancellation marks and such. So if you want to see this problem done in a more step-by-step way, that's what the YouTube videos are for. They could also be.
Parallel is not touching, right?
Sorry, say again? Oh yeah, parallel,
Is
exactly.
parallel touching or intersecting?
It would be non-intersecting, non-touching. So parallel lines we think of as being just exactly like you said, lines going like this. And imagine it's parallel. Let me try to draw it better. So these would be parallel. If they look like this, and this is hard to draw because now there's two lines on the same spot, so I made that line bold, this would be coincident lines. And the book's definition for this is to take this as not parallel unless they have different y-intercepts. So they would look like this right here. Key fact about parallel lines is the slopes had to be the same. So that's why when it said the line had to be parallel, and we saw that the slope was 1/2, we took the same exact slope for our line that we built. We made it 1/2 again. Other questions about that so far? Okay, well, let's try out our next problem for the day, and then that's the end of the section 3.3 notes. Kind of weird doing just one new problem and then closing out the notes, but I didn't want to rush through this on Thursday. That would probably not be helpful at all, really. So instructions are, we're going to find the equation of the line. Let's just retype that so we can visualize it. Find the equation of the line in slope intercept form that satisfies the following information. So that following information is the equation, the line we're going to build is perpendicular now to this one, 4x plus 3y is negative 6. And it has the same y-intercept as this other totally different line, 2x plus 3y equals 5. So before we even get started on this problem, we really have a couple steps we have to take. Step 1 is going to be to find the slope. And we're going to get the slope from this information right here. We're told the line that we are building is perpendicular to that exact line right there. So let's recopy it down below. 4x plus 3y equals negative 6. To find the slope of that line, we just put it into slope-intercept form. Those same instructions right here. That just means you're solving for the y variable. So subtract 4x from both sides. 3y is negative 4x minus 6. Divide both sides by 3. So our equation is now y equals negative 4/3 x minus 6/3. So this one has slope equal to negative 4/3. So we did it. We found the slope of this line. It's not the slope we're using. So that's why I didn't write m equals just yet. The slope we're going to use is the negative reciprocal of that one. So we have to flip it. It'll be 3/4, and we'll make it positive. Well, before we do that, let's now go over to this part and get the y-intercept. It said it had the same y-intercept. So that's the next thing we want to get. So step 2, find the y-intercept. Definitely a trickier problem. That's why we saved it for last. I believe this one is in the homework as well, making it one we really ought to do in the class at the same time. We're going to find the y-intercept. Same instructions as before, that we're just going to take the equation of that line, 2x plus 3y equals 5, then solve for the y variable. So now subtract 2x from both sides. 3y equals negative 2x plus 5. Divide 3 into all sides. And so now y equals negative 2/3 x plus 5/3. And this line has y-intercept, I'll abbreviate it as just int for intercept down here, equal to 0 for the x-coordinate, 5/3 for the y-coordinate. So in other words, you might just say b equals 5/3. So using all that information, we can put it together and do this part. Once we find the equation of this third line, our work is done. It has to be perpendicular, so negative reciprocal to this slope, same y-intercept as this equation here. So we can now say our line, let's say our new line, just as a reminder, this is yet a third line on this problem. Our new line has m equals, now it's said right here, perpendicular. And we found the slope. So to get from there to here, when we know it's perpendicular, our mantra is we want the negative reciprocal, but that means if it's negative, we force ours positive. If it was positive, we would have given a negative slope, and then we take the reciprocal. So this is positive 3/4. In other words, just flip it and change whatever the sign is. So that's the slope we'll use. And y-intercept equals to 0 5/3. And let's maybe say it slightly different. Let me just say it this way. And b equals 5/3. Now, we don't need the point slope equation of the line for this one, because if you have the y-intercept, you can just directly use the formula for slope-intercept form. It goes y equals mx plus b. Then our work is just about done. All we have to do is put in the value for m that we've just found, put in the value for b that we've just found, and we're done. The answer to this whole problem is y equals 3/4 for m, x plus 5/3 for b. This is in slope-intercept form, like the original instructions asked for, because y is solved for, isolated on the left-hand side. So we did it, folks. This one line, and this is the only line that exists in the entire universe, will be perpendicular to this one, and at the same exact time have the same y-intercept as this one. We did it, folks. Exciting stuff. You don't have to plot this all to make sure it looks all right. In fact, that's hard to do. You need really nice graph paper and a very steady hand to plot it. So doing it algebraically gave us the exact solution without having to worry about even plotting it at all. But any last questions at all, folks, with the end of the notes here? Okay, well, we're done in chapter 3. Congratulations, we've gotten through that one. Chapter 3 is intense in the sense that there's a lot of new formulas. Probably stuff that you've seen before, but you might have been rusty on them. It might have been a while since you've done the slope of a line, for example. Chapter 4 is not as formula heavy, so that's the good news. The tricky thing about chapter 4 is more the fact that there's applications in this one. 4.2 and section 4.3 will have applications. And by applications, that's just like a math buzzword of saying word problems. So we're going to take our first really strong look at doing word problems starting in section 4.2. But before we even get there, we have to know how to solve the equations that come up in those word problems. And this is what the equations are going to look like. They're going to be so-called systems of two linear equations in two variables. Chapter 3 had one linear equation in two variables, so really the only thing new here is that's two equations in the same two variables, x and y. So we want to know how to solve these, how to visualize them as a graph, understand the nature of the solutions, the things that can come up, all starting in example 1. First, the definition just says a system of two linear equations in two variables has this form. X plus b, y equals c is just the first equation. You pick a number for a, b, and c. And these are Greek letters just so that uppercase A is different from this one. Pick a different value, alpha, beta, gamma, maybe 3, 5, 0, for example, and you have your second equation. So that's what happened here with the 2, the 3, and the 12. Just imagine putting 2, 3, 12 in those spots, and you get that equation below. So that's what the equations look like. And really, before we go to solve these things, we have to know what does a solution even look like in the very first place. A solution is an ordered pair xy. But that's an interesting thought, because if you jump all the way back to section 3.1, let's do this, just that. That was one of the very first things we were doing after we discussed what is a linear equation, what's a nonlinear one. We plotted ordered pairs xy, like 3, -2 was right here. If we're solving systems of linear equations, points like these are what we mean by solutions. Kind of different, right? Where solution is not just a x equals or just a y equals alone. It's a value for both x and y at the same time. And that's because we now have two variables we have to account for all at the same time, both x and y. So here's a typical example we'll go through just to get familiar with this new concept. It has the system 3x plus 4y equals 1, comma, and then second equation, -x plus 2y equals -2. Sometimes it's written this way, where it's stacked with a little curly brace. Sometimes a curly brace is not there, sometimes it is. Other times it's just comma separated and written out linearly like this. Now what we're going to do is take the three different points given. We're considering this system of equations written horizontally and determining which ordered pairs are solutions. All of these are just pairs of x and y coordinates. We're testing if they solve either one of those equations. So here's what the work is going to look like. Starting with 1, comma, negative 1/2. Most important thought that you have to have is, we wrote over here, this is the x-coordinate, and this is the y-coordinate, so immediately x is 1, y is negative 1/2. We have to plug them into both equations. So starting with this one, we'll go 3 times 1 plus 4 times negative 1/2, and compute from there. So what we did is we plugged in the x-coordinate and the y-coordinate into those specific spots. Then just simplify. This is going to be 3 minus 2 when we multiply here. So this equals positive 1. We check the original equation. It's supposed to equal positive 1. So I'll put a little check here to say we're happy with that one. If it was not equal, right at this one step, we would have said over here, not a solution. Well, we still don't know if this is a solution. To have a solution, it must satisfy both equations. We mean both simultaneously. So we have to check on this equation too. It goes negative 1 plus 2 times negative 1/2. So save substitutions as before. Simplifying this one is going to give us a negative 1 minus 1. We get a negative 2 here when we work out the arithmetic. Checking up here, we got negative 2 as well in the original equation. So that's just another quick check to say we're happy with that. Then back at the top, we can say that this is a solution. The justification is just the work below. When we plugged in the x and y values into both equations, we got true statements both times. They both equal to positive 1, negative 2. So that's 1 down, 2 more to try out. Here's a next order pair to the next one. But any questions first on the process, checking the solution here? Okay, let's try out the next one. 0 1/4. When you see that, whether you write it down on paper or not, think x is 0, y is 1/4, because that's literally what we're going to do in the next step. Let me copy it here, 0, comma 1/4, just another point in the xy plane. We plug the information into both equations, so this will go 3 times 0 plus 4 times 1/4. Let me match up the color coding again, just for the sake of connecting the dots with our eyes. Simplifying, we'll have 0 plus 1, so it equals 1. As it ought to. We want to get it to equal 1, so we're happy there. But again, you can't celebrate early. This doesn't tell us it's a solution at all until we check the second equation. So same substitution as before. We're going to go negative 0. Negative 0 is just a weird way to write 0, plus 2 times 1/4. So here's the color coding for those substitutions again. This time it's just going to be 0 plus 1/2. So this equals 1/2 altogether, but it was supposed to equal negative 2. So I'll write here as a little slash. It's a little bit dramatic. Let me try again. That looks like a check mark. Let me try a third time. This little slash is now saying not equals 2, which means we didn't get it equal to negative 2. And so this one is not a solution. That deserves an exclamation mark. This is the first time it's come up. It's not a solution because of that part right there. If you get a not equals, it's broken. We don't have a solution whatsoever. So this already gives us a good idea. These are just 2 lines in the planes, which we can plot. That's what the last chapter was all about, plotting these among other things. And if we did have a solution, this point would have been on both lines. The fact that it gave us a not equal to 1/2 means that's false. So not a solution on that one because it didn't satisfy just one of the equations. So a solution satisfies both simultaneously. Non-solution means one of them didn't check out. Maybe both of them didn't check out. But one coming out as not equals is all it takes for us to say it's no longer a solution. But we'll try out one more just to get the feel for this. It'd be weird to leave this one alone. So here's the next one we'll plug in, a -2 for x, a -3 for y. Let's write it down below here, a little dashed line. So next one is -2, -3. We'll give a conclusion here once we check out what happens. Starting with this equation, we'll have 3 times -2 plus 4 times -3. Same exact substitutions as before, wherever x was or wherever y was. Take those 2 points, substitute them in. So now this is -6 minus 12. That simplifies down to -18. We're way off, right? -18 is nowhere in the neighborhood of the 1 that we're trying to get to. So we'll say not equals 1. We wanted that 1 to line up, but it's broken right here at this step. In fact, this is kind of like the best outcome. If you get not equals on your very first equation you checked it in, you are done. You don't have to do anything further because it doesn't matter if it's equal to -2 on the second equation, like up here. Doesn't matter if it's not equals to -2. If it's broken in just one spot, the whole thing becomes not a solution, just like before. So that's the hint for example 1, just kind of a warm-up process of how do you check your answers. This will be really valuable in section 4.2 if we check our answers to any of the word problems we solve, because it really is just doing this. We take whatever we said x should be or whatever y should be, plug it back into the equations that we build, and see if we can satisfy both of them, like in this case. If you can satisfy both equations at once, getting equals 1 equals -2, we say it is a solution because we matched up those right-hand sides. Well, next thing we're going to do on all the rest of the examples in section 4.1 is solve those equations. I have 3 methods. One of them is not very good, but it's for the sake of seeing what does this all look like visually when you find a solution. That's example 2, solving by graphing. We'll only do it once. Any questions at all before we give it a try? Okay, let's give this a go. So we want to solve the system by using nothing else but graphing. This is dangerous because we're not machines, we're not robots that can graph with high precision. So anything that's solved by graphing should be suspicious. We would almost always rather have an algebraic solution because we think of those as exact. Graphing and finding a solution is just an approximation. But nonetheless, it's good to see it done at least once because it gives us an idea visually, what do the solutions even look like? What does a system of equations look like? So in graphing this one, I'm going to color code a little differently. One whole equation is going to be blue. Another whole equation is going to be green. We'll start off with 2x minus y equals 4. There's lots of ways to graph these. You can find the x-intercept, the y-intercept if you prefer, and then just plot them on the xy plane. I'll do this by solving for y, getting the slope and y-intercept. So I would probably do it personally by subtracting 2x from both sides. Negative y is -2x plus 4. If you multiply both sides by -1, you just flip the left side positive to positive y. Multiplying this side by -1 will give you a positive 2x. Then it distributes over here to give you a -4. So this tells us that there's a y-intercept at 0, -4. And the slope n is 2, or 2 over 1 if you prefer. So this is ready to plot. Go to -4 on the y-axis. 1, 2, 3, 4. Got it? There's 1 point on the line. This says go up to. For the denominator, go right 1. So back where we plot that point, go up 1, 2, right 1 unit, and we would be here. So that's our second point. Then carefully draw that line. And there it is. Looks like it intersects right here exactly at 2. And so that's good information for us as well. This is the line 2x minus y equals 4. So one down, we have to plot the second one. But let's put in 2x plus 3y equals 12. And if you like, you could change up the strategy. Let's actually do that just for the sake of just review on this. Let's plot this one using intercepts. We did that, we would want to get to x-intercept, either first or second, totally up to you. For an x-intercept, the review concept here is the y-coordinate is 0, so 0 goes in there. Let me switch the pen to a different color for scratch work. We set the y-coordinate equals to 0. That means 2x plus 3y equals 12 becomes 2x equals 12. If y is 0, 3y is just completely gone. Divide by 2, and x would be 6. So we have an x-intercept at 6, 0. So that's quite far to the right. 1, 2, 3, 4, 5, 6. There it is. Now let's get the y-intercept. At a y-intercept, the other coordinate is 0. So instead of 0 here, we put 0 for the x-coordinate in that position. Then let me do the scratch work. I'll copy the equation below. 2x plus 3y equals 12. We set that part to 0. So all that's left is 3y equals 12. Divide by 3, and y equals 4. So that tells us the y-intercept is at 4. So let's go up 1, 2, 3, 4 on the y-axis. And now we're ready for our second line. So this is the touchiest thing about the whole process. I have to plot that 100% perfectly to get the exact solution that I'm expecting. If we were to read this off, it looks like our solution wouldn't be quite right, but we'd still do the best we can. Let's say what we can say here just from doing an honest by hand sketch. This is what a solution looks like. It's the point at which the line intersects. But you might be thinking already in your head, there's lots of ways lines can intersect. They could do it like this, or they could be parallel and never intersect, or they could be like the question that started us out today, where they're overlapping and they intersect at infinitely many points. Every point on the line is a point of intersection. Those are the three ways we could have things happen. This is where there was a unique solution. In other words, one solution, approximately. We're saying approximately here because we're omitting this is a by hand sketch. I wasn't trying to do it perfectly. I don't know if I could unless I had really, really nice scratch paper. It's approximately at xy equals, let's read this off for the x coordinate. It's at 3.5 would be my guess. The y coordinate of this point seems to be at 2. So that's what a solution would look like if we're considering it all graphically. Again, example 2 is not something that we do a lot in this class. I'll never ask you to do something like this on the second exam, for example. If you do this one on the homework system actually plots the lines for you perfectly, and then you just click on the point and read out the coordinates. It's a little bit easier using that technology. But the major thing we want to do is find out how to solve this exactly. So we're not just trying to put lines down perfectly. We're not approximating at any step. We'll know the exact solution every time, if there is one. But this is our warm-up to getting to that point. Any questions at all, folks, with attempting to solve the system just purely graphically? Okay, Before we show the algebraic process of solving these, there's a few concepts that goes along with this. It also justifies why did we talk about parallel lines in the first place? And then because we talked about parallel lines, we had to bring in the concept of perpendicular lines. It's because of all of this information right here. This is information that comes back as questions on the homework system itself. So this is a good place on the notes you might want to refer back to just to get a quick readout on this information. This is also a source of pretty common exam questions. I'll ask some questions that are similar to these on exam 2. And on the final exam, these kind of questions could come back as well. Let's read through this carefully. It's like a bit of vocabulary that we need to learn when we're getting into systems of linear equations. So it says, a system of linear equations has one or more solutions. We say that the system is consistent. So in other words, a consistent system just means it is solvable. A solution exists to it for that system. This one has a unique solution, so it's consistent. So we said here the system is consistent in blue. This one has no solutions. The lines are parallel. That one is an inconsistent system. So we said in blue here the system is inconsistent. And these are coincident lines or coinciding lines is how our author decided to write it. This means this is two overlapping lines. We only see one because if you plot two overlapping lines, well, they overlap. There's just one line now. We'll see an example of that just shortly in the notes. We say the system is consistent too, but note above, infinitely many solutions on this one, whereas on the left, no solution. Over here, one unique solution. So consistent just means there is one, like over here, or infinitely many, like over here. And these are the only three possibilities that can ever occur because our equations can't bend to intersect ever again. They're just straight lines. It's going in this direction for all of time now. Then last, an inconsistent system just means no solution. I guess that's already written right here, no solution. There's exactly one way that happens. The lines are parallel, non-overlapping. It would look like this. So that's the first block of vocabulary. Inconsistent versus consistent systems just means no solution versus there's at least one or infinitely many. Two more definitions to take a look at, but any questions with the information so far? Okay, everything we do really just comes back to this table right here. The next information is independent versus dependent lines. Dependent is a little bit easier. It happens in exactly just this way. If your two equations represent the same line, all points along the lines are a solution, and that's when your equations are dependent. So that's what happened over here. Two overlapping lines always results in dependent equations. That's the only way we can get them. But if the lines are different, like in this case, or even in this case where they're parallel, they never intersected, and the system is inconsistent, if the lines are different, that's when they're independent equations. So our goal is to put this all together, look at a set of equations and determine without graphing, determine how many solutions there would be, if the system is consistent or inconsistent, and if the system is independent or dependent. So example 3 is just learning this vocabulary again in specific examples, which is fair, right? This is hard to absorb unless we look at examples immediately. So that's what we're about to do. Before we do that, there are some hints to answering all of these questions. Let's extend this table a little bit. One unique solution, giving a consistent system with independent equations, this happens when the following. Let's write out this as just a key. M1 is slope of the first line. Say, for example, maybe this one's the first line going where the red dot is. M2 equals the slope of the second line. So again, maybe this one's the second line. When we have this happen, when they intersect at exactly 1 point, that means the slope of the lines are not equal. M1 is not equal to M2, or in other words, slopes are different. So that's the only way this could ever happen, having one unique solution. Then over here, parallel lines, that was our review concept at the very start of class. That means the slopes are the same. M1 equals M2, but a little bit more. The slopes are the same, but the y-intercepts are different. This is why they didn't overlap. This is why they're not coinciding lines. So slopes are the same, but different y-intercepts. I'll just write y-int for intercepts. And on this one, if your lines are coinciding, this means M1 equals M2, and the y-intercepts are the same. So there's exactly 3 things that can happen. In other words, a trichotomy, this one, or this one. It's all resolved by knowing the slopes, whether they're different in this case or the same, and also knowing what the y-intercepts, knowing if they're different or the same, gives you those 3 different possibilities. From there, we know everything about the solutions, how many they are, and this is the vocabulary part. We'll call it either consistent with independent equations, inconsistent with independent equations, or in this case, consistent with dependent equations. Well, there's only one way it is inconsistent, right here, and there's only one way it's dependent. That's helpful for our mind as well. Being consistent and being independent are the more common outcomes. These are the unusual cases, inconsistent and dependent equations. So with all that in mind, we're about to try out a problem. Any questions first before we try out to example 3? Okay, all of this depended on the slope and the y-intercepts. So first thing we want to do is take these equations and find just that. What are their slopes? What are their y-intercepts? So I'll color code like we did on the very prior example. Do the first equation in blue, second equation in green. Starting off with 9x minus 3y equals 12. And the absolutely major technique we need is slope-intercept form. That gives us everything we want to know. So on this one, solve for the variable y by subtracting 9x. Negative 3y equals negative 9x plus 12. Divide through by negative 3, which is our habit so far. We've done this a lot with these equations. Y is going to be equal to 3x minus 4. And this tells us M1 is 3. M1 is just referring to, like we set up here, slope of the first line. Then it's rinse and repeat. Same process on the second one. 3x minus y equals 5. Subtract 3x from both sides. Multiply both sides by negative 1. That converts this to a positive y, this to a positive 3x, and this one to a negative 5. So this one has M2 equals 3. Already that tells us something important. The lines are parallel on this one. There's no solution. So we have, well, we should be really careful with that. These lines are parallel too, and it has infinitely many solutions. But what's the second key? The different y-intercepts versus y-intercepts being the same on this one. The y-intercepts are negative 4 and negative 5. So let me write b equals negative 4 for short on this one. B equals negative 5 for short on this one. It has different y-intercepts, negative 4 versus negative 5. So we are in this outcome, parallel lines. That means there is no solution whatsoever. The system is inconsistent, but they are different lines, so the equations are independent. That's a lot to write. Let's put it down all in one line. No solution. Inconsistent system. Independent equations. So that's kind of nice in a way. If we try to solve this algebraically, it'd be no fun because there's no solution. We're going to get stuck at some point. Just by knowing the slope and the y-intercept, we know it's fruitless. This one has no solution, and we can just stop. That's what we're going to be doing on the next examples down below. But any questions at the moment before we try the part B to this? Sorry, let me scroll to the right spot there. I want to take a quick screenshot to help us on the next ones, so we're not scrolling up and down rapidly. Okay, let's try this out again. So new set equations, brand new scenario. First thing we want to do is get the slope of this one, which will also tell us the y-intercept. So negative 9x minus 2y. That's a weird looking 2. Let me fix that. Equals negative 6. Add 9x to both sides, so negative 2y is 9x minus 6. Divide through by negative 2. So y is now equal to negative 9 halves x plus 3. First one's done. Now we do it all over again on the second equation. But you know, if you looked at this really carefully, some people might have done this already in class. You would have a really keen eye if you did that. You might have noticed that the equation below resulted from multiplying by negative 3. If you multiply the equation in green, you would have gotten, let me try again. If you multiply the equation in green by negative 3, you would have gotten positive 27 plus 6 plus 18. You know, in a certain sense, they're the same equation. They depend on each other. They have a dependency relation. Multiply one by negative 3, you get the other. I bet you the equations are dependent because we'll have parallel lines. Slopes will be the same, and the y-intercepts will be the same. But let's keep on solving to check that out. Take 27x plus 6y equals 18. Subtract 27 from both sides. 6y is now negative 27x plus 18. Divide all three sides by 6. Y equals now, let's do some algebra on this. 3 goes into 6 twice, into negative 27 9 times. So yeah, reduce that fraction, you get negative 9 halves x. 6 goes into 18 3 times. And it's the same equation. The slopes are definitely the same. The y-intercepts are definitely the same. So that tells us immediately, if we were to plot these equations, it would look about like that. Maybe a different slope for sure, but it's just going to be one equation. These are coinciding lines. So this tells us there are infinitely many solutions. It also tells us, this is the weird one. Well, let's go in order. The system is consistent because it's solvable. Consistent system. And then the third thing is, in this case, when the slopes are the same, the y-intercepts are the same, equations are dependent. This is what we mean by dependent equations. It's basically the same equation. You could do a little bit of algebra to get from one to the other, or do a lot of algebra, solve for y on both of them, and you're looking at the same equation. We can just tie off this comment by saying this is since the slopes and y-intercepts are the same. So we went from no solution to infinitely many solutions. Probably the one down below is going to be when there is exactly one solution. But any questions at the moment, folks, with solving either one of these? Okay, this is the last one in the set, so let's give this a try. Two equations, and we have a freebie this time. This one is already solved for y, so with y equals 4x minus 3, we already have the slope, m1 is 4, b is negative 3. Let's look at the second equation. It looks funny because x is solved for. That's unfortunate because it tells us nothing about the y-intercept or the slope on this thing. We wanted y to be solved for. So let me recopy it in this order. 2y minus 8 equals x. This time, let's add 8 to both sides. 2y is x plus 8. Then divide both sides by 2. Y equals 1/2 x plus 4. And m2, meaning slope of the second line, is 1/2. The y-intercept, which we're naming just as a b for short, is 4. But the key thing about this is the slopes are different. Anytime your slopes are different, even just by a little bit, this is the scenario. They will eventually intersect somewhere, somehow, and it'll be exactly one point of intersection for a unique solution. So that's what's going on with this one. We can say one solution, because there's one solution, the system is consistent. And the equations are definitely different, so we say independent. Equations. So that's the nature of anything and everything that can happen when we look at two linear equations and two unknowns. Just one of these three possibilities will come up. And part C just happened to be the one that we tried to graph, having exactly one solution. Finally, what we're going to be doing next is actually solving these. So if you're dying to see what does it look like to solve these algebraically, those are going to be our next problems. But any questions at all, folks, getting through the ones we finished? Okay, so example 4, we're going to solve this system of equations, here it is on the left, using the so-called substitution method. There's two great methods for solving systems of equation. One is substitution, the other one is elimination. That sounds kind of rad in a way, but they each have their kind of best use case. Sometimes the substitution method works the best. Other times elimination method works the best. So as we solve these, kind of mention why one method probably did work better than the other. On this one, I like the substitution method really well because we can solve for the y variable really fast on that second equation. So here's what substitution method looks like. Let's separate these out into two different equations like before. I'm going to write them horizontally like a two-column system. 10y plus 34 equals x. And on the second column, negative 7x plus y equals negative 31. Now, between these two equations, well, I said it's easy to solve for y on this one. But even better, if I looked a little bit closer, x is solved for immediately on this one. It tells us the fastest way to solve this equation is to take this whole thing and substitute it right here for x. If x equals 10y plus 34, everywhere on paper, including right here, you can write in 10y plus 34. So that's why we call it the substitution method. We're going to take the green equation, go negative 7 times, x was here, but x is literally equal to this. So we substitute in 10y plus 34 right into that spot where x was. plus y equals negative 31. At this stage, we can solve for the y variable. We would start by distributing negative 7 into the group, negative 70y minus, and then we would remind ourselves that exams are open calculators, so I need a calculator too on this one. Give me a moment while I get one loaded up. I need a calculator because I'm taking negative 7 times 34, and doing that 7 o'clock at night just doesn't sound like I'm going to do that accurately if I attempt mental arithmetic. I get to negative 238 plus y equals negative 31. Now we can combine our like terms. Negative 70y plus y is going to give us negative 69y minus 238 equals negative 31. Next thing to do is add 238 to negative 31. In your calculator, you probably type it in like this one, negative 31 plus 238. We're going to get a positive 207. So negative 69y is 207. Now we're just about there. Divide both sides by negative 69. Coming back over here to our handy dandy calculator. Let me move that kind of in a better spot. We're taking 207, divide by negative 69, and it's a negative 3 exactly. We're not done. We have to express our answer in this form, an x-coordinate and a y-coordinate. We have half the information we need. But that's okay, because if we rewrite this equation, it went 10 times y plus 34 equals x. So y went into this position. I'm putting parentheses when I'm about to make a substitution. And we take the negative 3 here and just drop it back in. So if we're using two columns, one for one equation, another column for the other, the substitutions kind of crisscross in this sort of way. We substituted once so that we had just a variable y that allowed us to solve it. When we put a number down for y, we go back here into the other equation and just overwrite where y was for the negative 3. Now this equation in blue reads negative 30 plus 34 equals x. That means 4 equals x. And we're done. The solution is 4 for x and negative 3 for y. So 4 comma negative 3. Not interval notation. This time we're meaning one exact point. So this is context sensitive. If you're ever solving a system of equations, this is always going to be thought of just as an xy coordinate, like we listed up here. But that's how it goes. This is just the ordinary substitution method. When it works well, it's a fast process. When the numbers are slightly less friendly, like down below here, it can be a little bit more tedious, but we can still make it work. Any questions, folks, on getting through part A? Okay, let's try it out all over again then. Part B is same kind of situation, not as friendly in numbers this time. To start this out, you could change these equations. You could just divide equation 1 by 4. There's no harm done. Let's in fact do that. Let's put in a new equation 1. Divide by 4. Actually, let's maybe put this on a new page as well so it's not jammed up with the last problem. If we divide by 4 on the first equation, we'll get negative 2x plus y equals negative 2. This is kind of a hint on the elimination method next. If you don't like your equation, you can do a legal algebraic maneuver like this and just change it. Let's do the same thing with the other one. Divide by, well, 6 divides all the terms evenly. Let's divide by 6. Let me write it down there. If we do that, we would have negative x plus y is equal to negative 4. So same exact solution set, dividing by 4 on equation 1, dividing by 6 on equation 2 doesn't change it. Just make sure you divide both sides of the equation. That's the only way we could have a problem. Now, here's my equation 1. Let me rewrite on the left. Negative 2x plus y is negative 2. Equation 2, I'll write in the right to separate out. Negative x plus y equals negative 4. And interesting thing about the substitution method is you can pick any equation and any variable in any equation to solve for. It's really all up to you, and any method you take is going to lead to the solution. Me personally, I think I would solve this equation for the variable y. It looks like the most immediate way to go. Add x to both sides, and we'll have y equals x minus 4. That x minus 4 right here for y, it's going to go inside here. So let's recopy the equation. Negative 2x plus. Blue parentheses are where y was by the red dot, equals negative 2. And this whole thing, the x minus 4, just drops right in. So here it goes. X minus 4. Parentheses are sometimes just a way of organizing what goes where. But in the last problem up here, parentheses were more than that. We needed them to see the distribution of negative 7 with the distributive law to get that negative 238, or else we wouldn't have had the right solution. Best thing to always do is, more parentheses are just for safety, and it helps your eyes see where things go. Always a good idea to include them, especially if you're making a substitution, like we just did here. But these parentheses drop right away. This is just rewritten, negative 2x plus x. Minus 4 is negative 2. We can combine like terms. Negative 2x plus x is just negative x. So now it's negative x minus 4 is negative 2. Add 4 to both sides. Negative x is positive 2. Multiply both sides by negative 1. And then finally, x equals negative 2. And we're just about there. Our end answer is going to look like this. The solution is we need an x coordinate and a y coordinate. We're halfway there. Well, really more than halfway. We did most of the algebra. So this is the first half of the solution, negative 2 for x. Now what we do next is go back to the other column where the y equation is in green. Y equals value going in for x minus 4. So here's the solution. Substitutions kind of crisscrossing again if you're a fan of arrows, showing where things go. Combine those like terms, y equals negative 6. And then we just have to go down here to match the instructions. The solution where both of these lines intersect is only at this one point, negative 2, negative 6. So we did it, folks. That's 2 problems down. And this is how the substitution method goes. In the next section where we're solving the application problems, we'll often use a substitution method. But you know what? Almost half the time, we'll notice there's an easier way. Some equations have a nicer approach where doing this is more work than you really have to do. And that's why there is the so-called elimination method that we'll study next. Before we jump into the next method, any last questions whatsoever getting through this one? Okay, looks like we have time enough for just one more problem before we call it a night. So we'll come back when we're on Thursday's class to do the part B to these notes. Kind of like what we did on starting our last class. There'll be just one last problem before we go to the next section. You know, maybe that's not a bad idea. It's a good refresher before we do something new. So we'll leave that one for next. And next thing we're doing is the so-called elimination method. Let's look at these equations. First off, the real reason why you'd want the elimination method is, look at how you have an x and a negative x. It's tempting to just combine them. In fact, you can. There's lots of interesting things you can do algebraically in a system of equations. You could rewrite them. X plus 3y equals 9. Negative x plus 7y equals 1, and just put in one big tally bar to say, add them all up and see what you get. You could have done that up above here, except it wouldn't have helped us in any really big way. We would have just gotten a third equally complicated, maybe more complicated equation. So why are we adding them up here? Well, if you add them up, the x variable eliminates. And that's why we call it the elimination method. These two add to 0. Negative x plus x is 0, so gone, null, void. We don't need to even write it down. 3y plus 7y gives us 10y. Don't forget to add up the right-hand side. 9 plus 1 will give us 10. And so y equals 1 when we divide both sides by 10. We're already halfway there. Y equals 1 in our solution. It would go here. So the solution is, well, we just need to come up with the next variable. Let's color code this just to help see the eyes on the next step. Even though it's called the elimination method, you still do a substitution. So pick either equation. Usually you go for the one that just looks the easiest. We're going to plug y equals 1 into that equation. I'll start with equation 1. This looks easier because x is positive here. X plus 3 times y equals 9. Substitution goes there, so it's x plus 3 times 1 equals 9. Or in other words, simplifying the right-hand side, x plus 3 equals 9. Subtract 3 from both sides, and x equals 6. Well, that's the x-coordinate. It goes there. And we're done. That's kind of strange. I told you we had enough time. We have 3 minutes to spare on this one. Kind of weird, right? Sometimes the equations are set up just right, where the elimination method is very, very few steps altogether. Any questions at all, folks? Finishing off this one. Okay, well, elimination method doesn't always work. This is why we have 2 competing methods. The substitution method in example 4 sometimes works fantastic. The elimination method in example 5 sometimes works fantastic, like on this one, but both of them have their downsides, like we'll see in our coming next section 4.2. Downside for elimination method is it's sometimes requires setup and it doesn't always work out nicely. This is going to be one of the challenging problems that we're going to take a look at, where elimination method works, but you have to make it work for you. But I think this is a good stopping point for us at this point. Any last questions, folks, before we call tonight? Okay, when we come back on Thursday, then we'll just be right here. We'll finish off one more problem, kind of refresh and review what we've been doing. Then we'll go into this next section over here, 4.2, applications to systems of linear equations. Well, have a great night, folks. I'll see you all in Thursday's class. And if you have any questions on using the link to set up your time to take exam, don't hesitate to reach out to me. I'll be very happy to help out. But have a great night.